Hi, I am James Donglia 75106 who will explain about the engineering problem related to fluid mechanics problem. This problem is sourced from the textbooks which is Fluid Mechanics by Sengel and Hambala 2014. And in this problem, it provides a scenario involving a pitot static probe and the calculation of volume flow rate and Reynolds number of oil flow through a pipe. In the first question, pitot static probe is mounted in a 2.5 cm inner diameter pipe at a location where the local velocity is approximately equal to the average velocity. The oil in the pipe has density of 860 kg per meter cube and viscosity of 0.0103 kg per meter second. The pressure difference is measured to be 95.8 Pascal and calculate the volume flow rate through the pipe in cubic meters per second. The first question is involving calculate the Reynolds number of the flow in problems above and to state whether it is laminar or tubular. In order to solve this engineering problem and to calculate the volume flow rate of oil through the pipe, let's state the assumption. The firstly is the pitot static probe is located at a location in the pipe where the local velocity is equal to average velocity. The density of the oil is considered to be 860 kg per meter cube. Thirdly, the viscosity of the oil is considered to be 0.0103 kg per meter second. And since the volume flow rate is equal to average velocity times the cross-sectional area, then it can be obtained from the pitot volume pitot formula as stated below. To solve the second question of the engineering problem, which is to calculate the Reynolds number and to determine if the flow is laminar or turbulent, the assumption is the same as the above questions, which is pitot static probe is located at the location in the pipe where the local velocity is equal to average velocity, the density of oil is equal to 860 and viscosity equals to 0.0103. And from the pitot formula, we can get the Reynolds number formula as shown below. And to determine whether the flow regime is laminar or turbulent, we can get if the Reynolds number is more than 2300 is considered turbulence, but if it is less than 2300 then the flow is considered to be a laminar.
Hello, my name is Sheikh Umaimin bin Syazaidi and my metric number is 82926. So for the algorithm, first we need to calculate the volume flow rate by using formula V dot equal to pi r squared, square root of 2 delta P over rho, where r is the radius of the pipe. Then we also need to calculate the Reynolds number. We use the formula Re equal to rho dV average over mu, where V average is the average velocity of the flow. After that, we need to determine the regime. So if the Reynolds number is lower than 2300, the flow is laminar. But if the Reynolds number is bigger or equal to 2300, the flow is turbulent. After that, we need to visualize the relationship between pressure difference and flow rate over Reynolds number.
Hi, my name is Manisam and this is our first chart for calculating and visualizing fluid dynamic parameter. Our process starts with the following input, which is D is for the diameter of the pipe, Rho is for the density of the fluid, mu is for the viscosity of the fluid, and delta P is for pressure difference measured by the Peter tube. The first calculation we perform is to determine the radius of the pipe, so R equal to D over 2. Next, we calculate the average velocity of the fluid using the pressure difference and density. Next is using the average velocity, V average, and the pipe cross-sectional area, which is derived from the calculated radius, we can determine the V dot. To identify the flow regime, we calculate the Reynolds number, Re, using rho, V dot, D, and mu. The decision. Here, the program checks if the calculated Re is less than a threshold value, typically around 2300. And using this Reynolds number, we determine the flow regime. If Re is less than 2300, the flow is classified as a laminar. Otherwise, the flow is classified as turbulent. And for the output, the program display the calculated value for volumetric flow rate, V dot, Reynolds number, and flow regime, whether it is laminar or turbulent. Finally, we visualize the data using the plot functions.
Next, I will explain about the program design pseudocode. The program starts with begin, then enter the input of D, rho, mu, and delta P. Next, we also state the value of R, value of V average, and V dot, and the Reynolds number. If the Reynolds number is less than 2300, then the flow regime is considered as laminar, or else the flow regime is considered to be a turbulent, and that is the end of if-else command. And then we need to display the output of V dot, Reynolds number, and flow regime. And after that, we end the program.
Okay, for my part, which is MATLAB code, so the given data from the fluid mechanic problem, which is diameter 0.025 in meter, for density 860 in kilogram per meter cube, for viscosity 0.0103 in kilogram per meter second, for delta P value, which is range of pressure difference in Pascal. So I initialize a risk for strong result. For V dot values, Re values, flow regime, and then the loop through each pressure difference. For delta P is equal to delta P values. And then the next is for calculation. For radius is D over 2. And then for average velocity, I use square root of 2 times with delta P over rho. And then for volume flow rate, I use V dot is equal to pi times with radius R square times with V average. And then for Reynolds number, which is Re is equal to rho times with D times V average. And then I store the result. For V dot values is equal to V dot, and then Re values is equal to Re. And then I determine flow regime using if-else statement. If Re is less than 2300, so flow regime is laminar, or else flow regime is equal to turbulent. And then I display the result using fprintf. And then for the graph, I plot the volume flow rate versus pressure difference. And then for the x label, I use pressure difference in Pascal. And then for y label, I use volume flow rate. And then the title is volume flow rate versus pressure difference. And then I plot the graph, which is Reynolds number versus pressure difference. For the x label, I use pressure difference in Pascal. For the y label, I use Reynolds number. And then the title is Reynolds number versus pressure difference. The next is I plot flow regime graph. For the flow regime graph, For the X label is pressure difference in Pascal. For the Y label is Reynolds number. Then the title is flow regime versus pressure difference.
Hello everyone, my name is Muhammad Razia. I'm presenting with metric number 82749 and I will be presenting the sample output for our engineering programming project. Today I will walk through the result we obtained from our MATLAB code, focusing on key parameters like volume flow rate and Reynolds number, and how these results help us understand the flow regime of oil through a pipe. For our MATLAB code summary, the code functionality, our MATLAB code processes different pressure differences to compute the volume flow rate and Reynolds number. It also determines whether the flow regime is laminar or turbulent. And for the key variable is D is for the pipe diameter, rho is for oil density, mu for oil viscosity, and delta P values representing a range of pressure differences. And for the detailed output analysis, you can see in the table right here. And as the pressure the differences increases, the volume flow rate also increases. This relationship is crucial for understanding how pressure impacts flow rate in practical applications. This is the graph of flow regime versus pressure differences from our sample output. This graph categorizes the flow regime based on Reynolds number, giving a visual representation of the transition from laminar to turbulent flow as pressure difference increases. By observing the flow regime graph, engineers can design systems to operate within specific flow regimes to achieve desired performance. For example, in HVAC systems, maintaining laminar flow can ensure quiet and efficient operation, while in industrial mixing processes, turbulent flow might be necessary to achieve uniform mixing. Understanding and controlling the flow regime is thus essential for optimizing system performance and longevity. This is the graph obtained from the MATLAB output that we done. The graph is Reynolds number versus pressure differences. You can see here, the high pressure differences result in higher Reynolds number. This indicates a transition from laminar to turbulent flow as the pressure difference increases, which is critical for designing efficient piping system. And for detailed analysis, the Reynolds number helps us understand the nature of the flow, whether it is laminar, transitional, or turbulent. Laminar flow, characterized by smooth, orderly fluid motion, occurs at lower Reynolds number. As the Reynolds number increases, the flow becomes turbulent, which is more chaotic and can lead to a higher energy loss. Understanding this transition is crucial for designing systems that minimize energy consumption and avoid issues like pipe erosion or inefficient flow distribution. This is the graph of volume flow rate versus pressure difference. The graph clearly shows a positive correlation between pressure difference and volume flow rate. As pressure difference rises, the driving force for the fluid to move through the pipe increases, resulting in a higher volume flow rate. This is essential for engineers to design systems that can handle varying pressure without compromising flow efficiency. The graph helps us predict how much fluid will flow through the pipe for a given pressure difference, which is critical for applications such as pipeline design, fluid transport system, and hydraulic system. By using MATLAB to calculate and visualize these parameters, we can automate complex fluid mechanics calculations, making it easier to analyze and design fluid systems. MATLAB's powerful computational capabilities allow for quick and accurate processing of large data sets, enabling engineers to focus on interpretation and decision making rather than manual calculation. In conclusion, our MATLAB code provided valuable insight into the behavior of fluid flow in pipes, aiding in the design and optimization of piping system. That's all from me, thank you.